So thanks a lot for, just giving an opportunity to give the starting talks in this nice workshop. And the topic that I want to talk about is actually not my work, but I do some work on top of this framework called tensor-programs framework. So, and then I found this fascinating for multiple reasons. So what I'm going to talk about for the next 1 hour is some introductions about this tensor-program frameworks. Also, I want to mention a little bit about, I think, one of the kind of very active research activities in the theoretical the deep learning, which is about analyzing neural network at the infinite width limit. So you heard a lot about the success stories about neural network. ChatGPT is it's fascinating, but at the same time a bit scary. And then I know that there are lots of people from not just the machine learning community, but programming language community try to see where we can use kind of recent development of deep learning to solve some problems in programming languages and so on. So there are lots of success stories. But if you take a step back and think about it, it's a bit strange. One reason is that this usual large neural network have so many parameters. So in theory, what happens is that it just remember the training data and can fail to generalize. But the whole reason about doing the learning is to do the generalizations. So one strange phenomenon is that although the number of parameters is so large, if you train it, it can generalize and predict something new, or identify some patterns that exist in the data. So that's one kind of big surprise. And the other surprise is that, if you think about the outcome of this deep learning, it's very kind of nice, but the algorithm, engineering, it involves lots of new techniques, but the basic algorithm they are using is essentially gradient descent, which is a hill climbing algorithm for solving an optimization problem. So it's also quite surprising that this big achievement is done by a very simple algorithm like this. Especially the training often amount to solving some optimization problem, but what they are doing is solving optimization problem by hill climbing. So then often what you can achieve is the local optimum. But still, it performs extremely well. That's very surprising. So the people in the deep learning community, they ask the questions about why this is the case. Especially theoretically oriented people want to come up with some mathematical explanations that explains the generalizations and then the phenomenon of the deep learning. And it's still an open problem. I think that lots of people are working on it. But one of the kind of recent activities towards this direction that kind of grabbed attention of so many people is something based on so-called infinitely wide neural network. So the idea is that instead of analyzing this training and the generalization aspect of the finite neural network, if you just consider the limit where the number of hidden neurons go to the infinity, then maybe some interesting things we can say about it. That it turns out that is actually the case. So you can see some very simple-minded so-called perceptron, which have 2 hidden layers, and there are a few nodes. But it turns out if you send the number of hidden nodes to the infinity, so you make neural net larger and larger and larger, that all of a sudden, many of the complicated questions about deep neural network becomes quite simple. It still requires some non-trivial mathematical analysis, but it becomes quite simple and leads to some surprising result. One of the surprising results is that if you use the infinite width limits of the neural network and analyze the training dynamics, hill climbing actually, you can show that hill climbing actually achieves the global optimum. So you can achieve the 0 training error, which is also a bit surprising. And then the other thing one can do is that you can even identify the form of the solution. So you have an analytic form of the solution in certain kind of a neural net. So that can be done in the infinite width limit. So many difficult questions can be answered in the infinite width limits. And also, this infinite width limit result can also be applied to analyze finite width neural network as well. So that's kind of created a lot of excitement in the deep learning community. And then the things that I want to talk about today, which is Greg Yang's tensor program framework, is in this context, but it has some very much like a programming language flavor. So what he has done is that he took these results and then he Okay, so what he has done is that he proposed a framework which is essentially a very simple programming language. But then the reason he proposed this framework is that he wants to generalize many of these results on infinite width neural nets from particular architecture like CNN or multi-layer perceptron to essentially all the architecture that we can think about. So then how can we do it? And the approach he took is that he defined a programming language that can be used to express computations over the neural networks. The language is very simple because we are not expressing neural network code, we are expressing neural network computation. In other words, we are expressing execution trace, which is often very, very simple. So he has defined a language, essentially what you can do with the language is define straight line programs. But he defined the language in such a way that the language is expressive enough. You can express lots of computations of the neural net, which is forward computation as well as backward computation that can happen during the training. But you can even think about some other kind of computation there. But one interesting bit about his framework is that when you write a computation, it's all parameterized by the width of the neural net. I mean, if you're familiar with like a parameterized model checking, there is some number of parameter n, which parameterize number of threads. Something like this happens. There is a number of parameter n that parameterize the width of the neural net. So if we increase the width, single program can describe computation over width 3, width 4, width 5, and so on. So then what he proved is, he proved some very interesting result, which is what he call master theorem, which says that if you increase the width, then of course the meaning of the computation will change. But his language is designed in such a way that if you increase the width, it's always guaranteed that the meaning of computation at width 1, 2, 3, it all converge. And then he even be able to compute what the limit of the convergence actually look like. So his master theorem gives some constructive way to define this limit. And then it turns out this limit is directly related to the infinite width limits, infinitely wide neural network that I talked about before. And his framework led to the massive generalization of all the results that people have done before. And although, like my limited number of machine learning friends, they also said very highly about it. All of his publications are, done in machine learning, major machine learning conferences like NeurIPS, ICML, and so on. So let me just to grab your attention a bit more, to give you some some key works on this domain. You can see that, the reason I put this up is because I want to show the number of citations. Actually, the machine learning people do care about these type of results. The first is a really famous paper, the thesis by Radford Neal, which, he was a student of Jeff Hinton. 1995, he wrote a thesis about Bayesian neural nets. In that very important thesis, he proved that if you increase the number of hidden neurons in a shallow network, it converges to the Gaussian process at initialization. So then the next two things, in a sense, generalize this result from the shallow network to the infinite networks. They are not about training. They are only about initializations. I'm going to explain to you about where the convergence issues and some importance about initializations arises. So these are two other results which happened around the same time, 2018. One is the second paper is done by people in Cambridge. The third is done by people from Google. And then they show that the Radford Neal's results can generalize from shallow network to the deep network. And then the fourth one is actually also a very important paper, which is done by some people in France. And they kind of took the same kind of approach, and now they analyze the training. So then the very important concept arises from there, which is called neural tangent corners. So if you Google neural tangent corner, you can see the applications of that idea, not just in the machine learning the theoretical machine learning context, but also in very practical machine learning context as well. And then these two are the papers by Greg Yang. And then around 2019, he wrote the first papers on the tensor-programs framework. He wrote out 6 or 7 papers, each is very long. Like the first one is like 70 or 80 pages. And then but then he, in a sense, built his own, in a sense, research programs, which is about designing a language which is expressive enough, but have this kind of convergence guarantee so that people can use it to analyze computations of the neural net. So the first one is mostly about initialization, but recently he gave us some papers about how you can use this technology to do the kind of tuning the hyperparameters of the training in a much more elegant and nice way. Okay. So the plan of my talk is, really, if I talk about training, that would be perhaps grab your attention a lot more, but I think doing so is much more involved, so I have to talk a lot more complicated setup and so on. So I focus on the initialization part, but I will motivate it so that you can get some feeling about why this matters, especially for those people who cares about like probabilistic programming and Bayesian deep learning, Bayesian learning and so on. So I will first tell you a little bit about convergence of a neural network at initialization at the infinite width limit, and then I'll move on how these kind of results can be expressed in the Greg-Young's framework, and then tell you a little bit about his framework. Okay. So let me start with the convergence results of neural networks at initialization in the infinite width limit. So here's the setup. The setup is that we are thinking about width-parameterized and then randomly initialized neural network. Although I put these two phrases, width-parameterized, randomly initialized, that's actually what happens when you write the code in PyTorch. So you put the size of the hidden layer. So that's what specifies the width of the neural network. Randomly initialized, even though you don't know it, it's happening all the time. So that if the weights are not set to 0, it's set to, sometimes set to 0, but it's set to some random sample between 0 and 1, or there are some other schemes to initialize the weights of the neural network. So, and then I just bring that up because, making it more explicit helps us to understand the importance of this convergence result at initialization. So here, mathematically, what we are thinking about is the function fn, which is parameterized by theta n. Theta n are the weights of the neural networks. And then once you plug in, there's a specific parameter. Neural network defines a mapping from input, which is r to the d, and output is a real number. Okay? And then because it's parameterized by the width, and then if you increase the single neural network by changing the size of the hidden layer, you can define the same type, function of the same type, but it can behave a bit differently. Okay. So then there are two kinds of parameters. The one is a matrix parameter. The other are vector parameters. Matrices are just typical weights of the neural network. The vector parameter can be understood as a bias terms in the neural networks, or vector parameter can also arise for some other cases. And they are the trainable parameters. And then they are initialized a little bit differently because for the matrix, if you think about it, if you do the matrix multiplications, we are adding n numbers. So vectors are typically not, if you think about bias term, you are not adding n numbers. So their initialization is a little bit different. For vector case, we initialize by normal distributions with some fixed n independent standard deviation. But for matrix, we scale it by n. You don't need to understand this exact scaling, but you just say that if the width increases, the weights of the matrix gets smaller, typically, in proportion to the weight. Now, because of this random initialization, although we don't hardly say about it, neural networks actually is a random function. So if you, and then also it's parameterized by n, we are given a neural network defines a series of random functions indexed by n. Okay? So then the question we are interested in is that now this f1 is a random function, f2 is a random function, and so on. So now the initialization question is, suppose we increase n, is it going to converge somewhere, or is it will never converge? They are all going to be different. So that's the question that we are interested in. I'm going to talk about here. And also it's the question that machine learning people became interested in from the old days. So the paper that I mentioned to you by Redford Neal gave an answer in the 1995. It said that for the shallow network, it converged to something called a Gaussian process. I'm going to tell you what it is a little bit later. And then around, the other two papers, the following paper that I mentioned in the previous slide by the group from Google, also a group from Cambridge, they also show that actually, even for the deep network, the convergence happens. And then later in 2019, some people, I think maybe from Cambridge or some other group, they also show that the convergence result holds for the deep CNNs and ResNet. Okay, ResNet is like a multi-layer perceptron with some so-called skip connections. So you can see that like up to that point, if somebody showed this convergence result at initialization for a new architecture, that became a paper. But then like 2019, Greg Yang showed that actually that's true for nearly all the architecture using his tensor-program frameworks. So for me, the programming language approach is a bit like, instead of thinking about single program, we are interested in collection of programs. And we try to define a language to identify the collection, and we study what the entire collection actually satisfies. So in this, in terms of technique as well as in terms of the spirit, I think Greg Yang follows some programming language style approach to address these issues which machine learning people care about. And in all these cases, so Greg Yang did a great work, but in all these cases, they were able to show it converged to something called the Gaussian process. I think some of you are familiar with the Gaussian process, some of you are not. Gaussian process is a functional generalization of multivariate Gaussian distribution. Gaussian distribution, again, if you haven't heard about it, it's a bit scary, but what's really happening is that that's one of the best probability distribution for which we can do posterior inference exactly. Okay? So what that means is this Gaussian process is the one for which we can perform. These are the random functions for which we can compute so-called posterior predictive exactly using some formula. Okay? And in all these results also identify that this Gaussian process is specified by these two parameters. One is called mean function. The second is called the kernel function. These results tell us how we can derive this mean function, kernel function from the architecture of the neural networks. Okay, so I gave a talk like this before, but then people were puzzled because they said, okay, who cares about initialization? So I want to say a few more words about this. So the reason, there are perhaps multiple reasons, but one reason that somebody might care about this initialization is because it's closely related to the so-called Bayesian neural networks. Okay? And in Bayesian neural networks, we are viewing neural networks as a random function. And then we are viewing training set as an observation. And then what we do, the training in this context corresponds to the posterior inference. So if you perform the posterior inference, we have a posterior distribution on the random functions, which is neural networks. And we are using this posterior distribution to do the prediction. And it turns out, people think that this is the more principled way of achieving uncertainty estimates in the neural network, which is one of the biggest challenges for the neural networks. But it's hard, so that's the reason that people don't do it very often. But it turns out if this connection between the infinite width limit connection at initialization help us to address these difficulty issues with the posterior inference in the Bayesian neural net context. I'll tell you a bit more about this. Okay. So as I said, in the Bayesian neural networks, the training data set, think of it as input-output pairs. Suppose we have m input-output pairs. Then the training in this context corresponds to the posterior inference. So although I talk about random functions, because it's finite, it's almost equivalent to think about posterior distribution of the parameter. So theta n is a parameter of the neural nets at width n. So we are computing the posterior of these parameters, and that's in proportion to the prior, which I told you, IID Gaussian, and the matrices are kind of almost the Gaussian with the appropriate scaling with respect to width. So that's the prior distribution. And then we have a likelihood terms, which say that the observations in my training set should be pretty reasonably close. It gets a score if the prior sample theta n, the neural network, the predictions with the sample theta n on input x is reasonably close to y. So it's a Gaussian distribution for y. Mean is the prediction of the neural net at the current sample theta n, and then sigma, the square, talk about some noise in the prediction. Okay. So it's a typical Bayesian inference things in the, and then, so this is what people think when they talk about the Bayesian neural nets. So some people run MCMC algorithm like HMC or Langevin dynamics to generate samples like posterior sample theta n. They use these posterior samples to make up predictions about the new input. So that prediction is done by one below. So if you have some new input x0 and want to make a prediction about it, in the Bayesian neural net context, we are not making the point prediction. We are making prediction in terms of a distribution. So we are saying what's going to be the distribution on the output for given x0 or conditioned on the training set. And that's defined by the typical integration formula, which say that the output should be close to the prediction by Fn with parameter theta n, but the parameter should be sampled from the posterior distribution. So you are thinking about posterior, the conditions, neural network random functions, and you collect all of its predictions. And then by collecting all of these predictions from the posterior neural net random function is going to be the appropriate prediction. And you can think of, if you compare this with what's happening in the typical deep learning, you can see the power of this. So in the typical deep learning, with more specifically regularized training with mean squared loss, what people do is that instead of computing the posterior distribution, they compute the theta n that maximize the posterior distribution. So they do is so-called map inference. And then the prediction of the output is just with respect to the single, the maximizing theta n. So that's what happens below. So you can see that Bayesian is much more ambitious. And then if you can do it, if we can do it, then we can have a lot more information that is good about, because we have a much better the information in terms of probability, it can have the better uncertainty estimate, how certain the neural network is. Okay, so, but as I said, this is like a much more difficult problem. So usually it's very hard. And I think some people are working on this. But at the infinite width limit, it turns out that becomes really simple. So if in the infinite width limit result are all of the form, if we increase Fn, view this as a random function, it converges in distribution to a random function f, which is a sample from the Gaussian process. As I said, if you already know it, great. If you don't know it, doesn't matter. It's a generalization of the normal distribution for which we can do many calculations analytically. In particular, what we can do is that this is very similar to what I showed you before. It's a prediction of this trained neural network for on the new input x0. And that's done by taking the posterior samples of f of the neural network and compute its value at x0 and then add some noise. That's how we generate this new input y0. So that's exactly the same formula as before using the random function instead of parameter. It turns out this integral is tractable. So we can compute this integral, and then this p of y0 given x0 and data d is actually a normal distribution. And then its mean and standard deviation can be derived. It has an analytic formula that can define the mu and sigma square. And they are related to this data point as well as this mean function and the kernel function. Okay. So, yeah.
Are you fine taking questions now?
Yeah.
So if we're training, oh yeah.
Hi, Hongseok. This is a great introduction, by the way. Is this on?
I think so.
Yeah. Closer. Yes. Hi, Hongseok. So I guess my question was, if you're computing this type of Gaussian process posterior, then usually you have to invert some matrix, which is size of the data points by size of the data points. And so somehow it seems like there might be a problem when you're trying to do this in deep learning, where the number of data points is 1 billion.
Yeah.
So these results from LAFI'23, because I'm actually not familiar with them, like what type of data set sizes do they look at?
So I forgot what they are using, but the most recent, around 2020, they tried to apply these things to the real world data. And then I think they do the usual trick, like induce points and so on. So they do some approximation. And I think they applied it to the real world data set. And what they found is that, what Jan Willem pointed out, Gaussian process, yes, there are analytic formula, but computationally it's expensive. So you need some further approximation to address this computational issue. And it turns out that if they just use what the Gaussian process people already developed, maybe a little bit more, but then you can do almost state-of-the-art the performance during 2020, which is a bit surprising. People designed the Gaussian product with specific M and K, well, especially specific K, to define a better Gaussian process. But this K derived from the neural network leads to the very good Gaussian process. Okay, so the point is, I mean, this is at least useful in practice as well. But I think also like theoreticians I mean, this is a basis for analyzing the training. So like there are multiple reasons we care about this type of result. But now to apply this result, what we need is we need this type of convergence result. And then as I showed you before, like before Greg Yang's work, people proved it one by one, F1 architecture and so on. So, and then also they derived what M and K actually look like. But it would be ideal that if we can have some framework that allows us to derive this Gaussian process result as well as M and K once and for all, in some sense, for large number of architectures. So that's what Greg Yang did, and that's what I want to explain to you now. Okay. Right. So the Greg Yang's framework, he defined a programming language, very simple programming language, which describes width-parameterized neural network computations. Okay. So here I only kind of use the forward computation only, but it doesn't have to be forward computation. Any computation over the neural networks that comes from forward computations, which is just running the neural network, backward computation, which is a back propagations, or some combination between the two or anything, that can all be written in the Greg Yang's framework. I mean, not all, but the large number of computations can be written in his framework. And but another important bit is that it's not about the high-level programming language which have if-then else, while loops, and so on. It's more about language for expressing execution trace, which is a sequence of assignment and so on. Okay. So in that language, if the program P, for instance, can express the random function, neural network random functions, evaluated with respect to the multiple inputs. I mean, this is actually quite important because to compute the kernels in the Gaussian process, we need to think about two computations at the same time. So multiple inputs. And then what it guarantees is that it always guarantees that this family of computation, if we increase n, so this result is a real number, if we increase n, it always converges to the Gaussian distribution. Okay. So that's guaranteed automatically. So it's a language is restricted. The restriction guarantees that this automatic convergence to the Gaussian distribution. And then furthermore, then the Gaussian distribution is specified by the mean and the covariance matrix. And it tells us how you can derive this mean and covariance matrix from the syntax of the program. It's not computable sometimes. It involves some expectation calculation, but it gives us some formula. So in some sense, what happened is that for this simple program, he's defining a family of semantics for each with parameter n. So n is equal to 1, we have one semantics, n is equal to 2, one semantics, and so on. But also he gives us semantics when n is equal to infinity. And it's guaranteed that if you increase n, this P, the semantics actually converge to the infinite case. They are all random variables, so this D means convergence in distribution. But I mean, again, if you don't know, it doesn't matter, okay? So let me illustrate the Greg Yang's example of tensor program for very simple computation which is a multi-layer perceptron. We have 3 layers, hidden layers. We don't have any bias term, and we have an input X. And this is Greg Yang's the representation of Greg Yang's some example of Greg Yang's the tensor program for this multi-layer perceptron. So in this case, in this program, we have 3 kinds of variables, but here you can see only 2. One is the matrix variables. Dimension is n by n. So the n is the width parameter. And vector variable parameters by n. So don't be fooled by W1x. This is just a single variable whose name is W1x because that's typically what corresponds to typical case. Okay? But there are 2 input vector variables. They are all random. And then inside the program, we don't really create any new matrix variable. We only create vector variables. But the way we create vector variable is either by matrix multiplications or application of nonlinear, pointwise application of nonlinearity. So then in the first case, we apply, this W1x is a vector, n. So we apply this activation function like a ReLU to the pointwise to the n-dimensional vector. And then we get H1, which is an n-dimensional vector. So that's what happens after the single layer, the first layer. And then the other two, we take the vector, which is coming from the first hidden layer, apply the matrix, and then we apply the nonlinearity to get a value after the second layer. And then similarly, we do the same thing to get the value at the third layer and so on. And then finally, for the output of the third layer, we do the linear combination with appropriate normalization to make a prediction. So suppose this neural net try to predict the real value, and that's what we can get here. So, I mean, for this case, it looks very much like a neural network that you write in PyTorch. But as I kind of pointed out a few times before, this is the language designed to express neural network computation. So it doesn't have any if then else, because if you run the program, you only have a sequence of assignments. Okay. So here's a bit more involved example. So we are thinking about the RNN on the two inputs. One is the input sequence of length 3. The other is input sequence of length 2. This is very simple-minded RNN. So for input x1 to x3, they are all transformed. I mean, this doesn't have to be linear transformation, but they transform first using parameter u. And then that transformed part is fed into the essentially a state machine, which is what RNN is. So the initial state of the state machine in the first case is set h1, and then it gets transformed by the second input, transformed by the third input, and then the final state is used to make a prediction. The same thing for y1 and y2. Initial state is set by using y1 and becomes h4 and transformed to h5 and so on. And this can also be expressed using the Yang tensor program framework. So we have an input, which is the W, as well as all these transform. The V is the one which is used at the end to make a final prediction. And all the others are related to the inputs. And then the first series of assignments, they are talking about computations on x1, x2, x3. And then the second talk about computation over y1 and y2. And the final bit is that we just combine the hidden states after the processing the first sequence, which is h3, hidden state after processing the second sequence, which is h5. We use them to make a final prediction. Okay? So these are the kind of things one can write. I mean, using the simplest version of his framework. So let me just tell you a little bit more about the syntax for the simplified version of his language. We have two types of vector variables in the language. One is called Gaussian vector variables. That's a dimension n. The second is, it's not necessarily Gaussian. That's what the right expression is. But I call it non-Gaussian vector variable, which is also the n-dimensional. And there are matrix variables, which are all n by n. And then they are all parameterized by the width. Okay? So that's in a sense, variables that can appear in his tensor program framework. And the syntax is really simple. Essentially, the program in his framework is command followed by the return statement, but command is the essential sequence of assignment. But there are two kinds of assignments that appears in his framework. The first is the Gaussian vector variable get assigned to the transformation of non-Gaussian variable by the matrix multiplication. So if you multiply the matrix, it becomes a Gaussian. It can be used to update the Gaussian Gaussian vector variables. Non-Gaussian vector variables is obtained by applying this activation function to the Gaussian vector variables. Okay? So essentially, assignment, there are two kinds of assignment. One is by matrix transformation. The other is applying the activation function pointwise. If you apply activation function pointwise, we get non-Gaussian vector variable. If you apply the matrix, we get Gaussian vector variable. Intuition is that if you increase n to the infinity, Gaussian vector variables becomes the infinite vector where each element are distributed by Gaussian distribution because of this CLT. The central limit theorems happens there, that it converges to the infinite vector where each component is distributed by the Gaussian variables. Non-Gaussian, I mean, typically is that kind of guarantee doesn't really hold. It's, yeah.
Yeah, sorry to interrupt. I have one clarifying question, if I may. So I see that the linear expression can be a weight times an h, and an h is a not necessarily Gaussian variable. And then in the commands, I see that G can be assigned through L.
Yeah.
So can you take something that is non-Gaussian, multiply it by a matrix?
What happened is, I mean, a finite case, the vector is not a Gaussian coordinate, but in the limits, that non-Gaussianity all disappears. Also, they are dependent with each other. In the limit, this dependency disappears. So the limit is really nice in the sense that it removes the dependency. It also kind of makes things to the Gaussian. So anyhow, that's in the semantics. I mean, what I'm telling you is intuition. In semantics, you can just view it as like, oh, it's a vector, matrix vector multiplication, pointwise application of the real functions to k parameters. Okay. And then you can assign some simple typing assignment, which say that if I have a program P, which returns m tuple that uses a matrix variable W1 up to WP, and the Gaussian vector variable G1 to GQ, and then some Gaussian variable. By the way, all the assignment there has to be the single assignment, so no variable should be assigned more than twice. So really, I think you may make it more explicit by designing language more PL style, but that's what happens here. Okay. So, and then everything is indexed by n. But then what's going to be the semantics? The semantics is defined first, the initialization, how we're going to initialize these input, the matrix variables and input Gaussian vector variables and so on. I mean, I wrote something complicated, but it doesn't really matter. Most of the things are assigned by IID Gaussian. Okay. There are some difference, but essentially they are all assigned by IID Gaussian. Matrix case, we scale it using the width. These are the two information. IID Gaussian, matrix case, we scale it by n. So these are the two key information there. And there are some specification. I mean, this part of the specifying the semantics or part of the job the user have to do is provide the distributions on the input, but they have to do it as an IID Gaussian essentially with the appropriate scaling. And then for the semantics of P, it's really simple. I mean, it's a straight line program, so it's just a typical semantics that you can write. I mean, if you just sit down and compute, it's very easy to write compositional semantics for a finite case. It's not a problem. Now, once you do it, then we can define the distributional semantics of the entire program because we have a semantics for the distribution on the input. We have a semantics of P as a deterministic transformation function. So if you put them together, or push forward measure, then you get a distribution on the output. Also, more precisely what happened is semantics of D, which is a distribution for n case, is a distribution on the output, the m tuples. That's defined by, for any event, you take an inverse image using P, and which then it becomes an image, some property on the input case. You just measure the probability for that. Okay. So now what we have, right, is that for every width n, we have this distribution on the output. It comes from the distribution on the input case. And then we can ask whether if we increase n, is it going to converge somewhere? If we converge it somewhere, where is it going to converge? It turns out, in this framework, it always converges. So it weakly converges to some normal distribution. Again, if you know what it means, great. Don't know, then doesn't matter. It converges to the normal distribution. And then furthermore, it's a mean, which it's an m-dimensional normal distribution. It's a mean, which is the m-dimensional vector. Covariance, which is m by m vector, the matrix. they can be computed in some sense semi-analytically using the syntax of the program. Okay, so that's what I meant by infinity semantics in the previous slide. Right. So that's what he called master theorem, and he used these theorems to show to generalize the result on the infinite width neural network from specific architecture to the general architecture. So then let me show you how the theorem works. Okay. So this is the multi-layer perceptron example that I showed you before. So let's try to apply his theorem. So his theorem actually tells a lot more than what I just told you. It's just what I told you before is that for the output, m tuple output, which is a random vector, if you increase n, it's going to converge to the Gaussian distribution. That's what I told you. But he actually tells us like every H1, the G2, G3, H2, H3 in this example, if you increase n, they're going to become an infinite dimensional vector. And then he said that the coordinate of this infinite dimensional vector will become independent. And it tells us what the distribution of each coordinate actually look like. And then so he assigned random variable z for each of the vector variable in the program. And then he kind of tells us how you can compute this random variable z. So z, distribution of z, for instance, the H2 tells us the coordinates, the single coordinate of H2 in the infinite width limit is going to have specify the distribution of what that single coordinate will have. So let me tell you how we can, what happens if you apply the theorem. So if you apply the theorem, so g's are random variable on the real number. It's not about vector, it's a real number. And it describes what's happening in single coordinate. Okay? So GW1X, which is about input, is really coming from the specification of the input. So it say that this is really coming from the specification. User specifies this, so it's not coming from the tensor program. User specifies this. And then for H1, we have to define something. But then the theorem tells us for H1, we look at the random variable for each argument, which is W1X, and we just apply phi. The ZW1X, the real valued random variable. So if you apply phi, we get another real valued random variable. That's going to be the real valued random variable ZH1. And for G2, now for this non-Gaussian case, we just applied this nonlinear, the activation function. But for Gaussian case, we are introducing new random variables. So in this case, we are introducing new Gaussian random variable. Mean is always 0, but standard deviation has to be computed in a certain way. And then in this case, standard deviation is computed by, has some variance has a contribution from W, which is a sigma W, as well as its argument, which is a phi of ZW1X. This is a random variable. So we apply phi, and then we take an expectation of this value. That's going to form the variance of this. I know that, this may be very too abstract, but there's just some systematic way to compute this. And other interesting bit is that now, if you look at it so far, you feel like, oh, this looks like a probabilistic program. But the difference is, the probabilistic program, we are not really computing the expectations when you are defining a model. Right? Some language you are doing marginalization on the fly, but we are not quite doing it. So this is a little bit of the difference between typical probabilistic model in probabilistic program and what's going on here. Other cases are very similar. H2, where we apply phi to get a new random variable. So you can see there is a dependency between z of G2 and z of H2. But the z of W1X and z of G2, they are independent in this model. And G3 defined similarly with, and then, so it goes on like this. So for each of the statements, it tells us how we can compute the entire program. So roughly, the way we compute is very similar to what's really going on in the program, except that for linear case, Gaussian case, we have to be a bit more careful, and there are just some rules about how you can do it. And at this point, you might think that, oh, this just shows that they are all independent, the Gaussian. So you think, oh, maybe if you do it, always we get the independent Gaussian. That's really not the case. For instance, if you change this W to W3 to W2, so that W appears twice, so then there's a dependency between the two. And then his framework tells us how we can compute the dependency. So it's two random variables are defined at the same time, means 0, but there's a covariance matrix. These two random variables, they depend with each other, and there's some systematic way to compute this dependency. Yeah, I'm almost done. So then, I don't want to tell you about this proof of this theorem, which is not so easy, but there are some reasons why you can feel that something like this happens. One is that, maybe some of you heard about so-called central limit theorem. Roughly, the idea is that although the single random variable is complicated, if you add lots of them and then take the average in some sense, things become nice. It becomes converged to the normal distribution. So there are so many things, then all of a sudden complexity disappears and some regularity start to appear. So that's what's captured by central limit theorem. And the reason why he was able to have this type of semantics and independence, all the nice properties, because implicitly his language is designed to guarantee central limit theorem is applied very well. And there are more subtleties about this proof, but roughly the idea is that central limit theorem plays a key role here. And his actual framework is more complicated. It's still straight line program, but for linear expression, we can also apply the transpose of the matrix. And this is really needed when you compute the backpropagation. And also, you can compute we have another kind of variable called scalar variables. And scalar variable is computed by taking the 1 over n, the average over 1 over n. And then that scalar variable can appear in the nonlinear expression. So this scalar variable can be used to capture some the value of the loss functions when they encode the training in this setup. And then the Bessa theorem still holds, but now not just the central limit theorem, but the strong log large number also start to play a role here. Okay, so let me just finish my talk with the two final remarks. Okay, why I want to talk about this? I thought, I myself is a user. Like I have one paper which uses this framework for it's an analysis for certain simple infinite width neural network. Some other ongoing work I'm doing is also uses this framework as well. So it's useful, but at the same time, it poses some nice research opportunities. So especially if you apply the framework for complicated neural network computation, the result you get is very complicated. It's a bit like you have a very, very complicated formula. It's about the reasoning on the level of execution traces. But we know that if you do some reasoning on the level of execution traces, it can become quite complicated. So people in the verification community come up with the idea of loop invariance and various other approximation techniques. So can we somehow use it to automate some of the calculations, especially the complicated applications of his framework? And then second, his setup is general, but still limited. So if you use the reason is that maybe the central limit theorems or this kind of argument doesn't work for all the programs. So maybe we can use types to identify where this type of argument can work. Finally, ultimately what we want to reason is on the high-level language. So his language is a low level, so can you do it high level? That'd be great. So it's my last slide. If you are interested, I suggest you just Google these keywords, then you can find some relevant paper. Okay, so that's it for me. Okay, thank you very much.
All right, thank you so much. So we have some time for questions, yeah. Please introduce yourself. I'm going to give you the mic, by the way.
Hi, I'm Eric Atkinson from MIT. So I'm just trying to understand. So your analysis has this assumption that each index row of the vector is independent.
So no, each index row are not independent in the finite case, but if you send n to the infinity, they become independent. So the dependency is so weak. So if you increase n to the infinity, it starts to become weaker and weaker. In the limit, it disappears. So that's what happens in the infinite limit.
Okay. All right, thanks.
Hi, I'm Matin Ravami, MIT.
Yes.
I wanted to ask, what class of activation functions are you considering for the master theorem to work?
So I think in the most recent work, he uses so-called pseudo Lipschitz, which means that it's like a Lipschitz, but instead of bounding by the x minus y, it can be polynomial. So that's the setup I think is using in the most recent paper, where he talked about feature learning.
Hi, thanks for the great talk. I'm Alex Lev from MIT. And I'm wondering, in the Gaussian process results you showed, you were talking about RD to R random functions. And a lot of neural networks need to output multi-dimensional outputs in order to reason about classifiers or any other sort of multi-dimensional regression task. Is there a version of these theorems for when you have more than one output?
So because the output, I put particular output to state the theorem in my slide in a simple way. But really reasoning is about what happens in the middle of the computation. So I think this type of the multiple output won't really matter. That's my impression at the moment, but who knows, I may be wrong. Yeah, but likely it's not going to cause a problem. If you use a different architecture like the one that I'm studying with my colleagues, then its coordinates are not independent sometimes. So there are, if you use a more kind of recent architecture or the experimentary architecture, it's not covered by his framework.
Hello, it's Eric again. So yeah, as someone who's not super familiar with these neural network Gaussian processes, I'm really curious what the performance is like of the infinite limit Gaussian process versus the finite neural networks. Like how much interesting stuff is happening when you take the limiting case and make it more complicated?
So for the practical things, I heard the finite width limits, the finite neural network with with many tricks, it works better than the infinite width limit. So infinite width limit case sometimes work better than the best Gaussian process example. But for typical examples, the finite cases works better. But understanding why it works better is something that people are working on it. But one other thing that I heard is that suppose you are in a regime where the number of data points is really small, so the Gaussian process is a kind of natural kind of fit. Then in that case, I heard something that arises from this infinite width analysis actually leads to the pretty almost state-of-the-art result.
Cool, thanks.
Hi, Zenith from Basis in Columbia University. So one of the intuitions that people have about finite width neural networks is that as you increase the capacity, there's like just more ability to like memorize or store information. And so what I lack an intuition about is how does that translate to this infinite width? Like,
So the infinite width limit, although there are some other stories which is about, so far I only talk about predictions, but what you're saying is a bit related to the feature learning. So the reason why we train the neural network is not just about making the predictions. We want to learn about feature extractor so that we can use it because that involves information about the data and then that you can apply in a different context. It turns out for some of the convergence results are incompatible with the feature learning. So there are some specific parameterization called NTK parameterization. If you do it, you have a very nice theoretical properties, but at the same time, you don't do feature learning. But if there are some different parameterization, then maybe some of the theoretical result disappears, but feature learning can happen and so on. So people are still exploring whether this infinite width limit captures all the nice aspects about the finite neural network. Maybe not, but they are trying to explore many dimensions.
So I'll do one more question if I may. So I'm Jan Willem van der Meent, University of Amsterdam and Northeastern. So thanks for a great talk. This was really a fantastic introduction. I think you could tell also from the questions. So what I took away from your talk, because I hadn't read this particular literature, is this idea that elements in your representation become statistically independent in the kind of infinite limit. And so my question is, how quickly do you start approaching that infinite limit? Right, so should we, for all intents and purposes, think of components as vectors as uncorrelated in most neural network architectures, or are most kind of commonly used architectures quite small, and would you have to make them a lot wider in order for these limits to kick in?
So I forgot the exact numbers, but most of these papers, let me just mention two things. Most of these papers talk about experimentally their results are not, only for the limit. That they increase the width enough so that, and then they show that something like this actually happens in the wide network, maybe 1,000 neurons or more than 1,000 neurons. And the second point is that independence is not necessarily the good thing. When I had communicated with Chae-Hoon Lee, the people in the Google, he doesn't really like, or he said one of the limitations is the independence, actually. So he asked me whether we can come up with something which captures some dependency. If you think about finite network, actually neurons depend with each other. It captures some different aspect. Yeah.
I had a question.
Yes.
So I think it's really interesting that, reframing this whole agenda in terms of programming languages, because I'm wondering if, that can yield, which sorts of insights that can yield, right? One in particular I'm kind of curious about is tractability of these particular inversion operations, for example, when you're computing these closed form means and stuff. Do you think there's opportunities within program analysis to focus on those tractability kind of questions, or give guarantees there, or leverage program structure in some way to make that more scalable?
So for actual neural net design, I don't really know. But for programming language, the approach that I kind of pushed forward was this type of idea can generalize existing result to the arbitrary architecture. But now I felt your question is more related to say, suppose I want to apply program analysis, what can you do more? And then one thing that I saw is that, when I looked at the most recent work of Greg Yang, he analyzed like a training up to arbitrary depth. So then if you think about training up to arbitrary depth, like depth k, that means that the execution trace is really long. So then the key way of getting some insight is to identify recurrence and solving some information about the recurrence. And that's very much related to the reasoning about loops in program verification. So although I don't have any proof, that maybe if you go beyond a single step and then like say arbitrary k step of the training and want to say something about it, then maybe some techniques from program analysis can be useful.